Hello all, welcome to lectures of Power System Operation and Control. We are discussing Unit 5, Economic Load Dispatch and Unit Commitment. And in this particular lecture, we are going to discuss, though very small but very important concepts in overall power system operation and control, which is concerned with uh, various power generating unit operations, constraints on unit commitment. These are the learning outcomes. At the end of this lecture, you will be able to retrieve some concepts of unit commitment or a concept of unit commitment. We'll understand what are the various constraints on unit commitment, and then you can divide or differentiate those constraints into typically for thermal units, then hydro units, and there are some other constraints. So let's understand what is the concept of unit commitment. I would like to focus on word commitment basically. The meaning of commitment is to bring any power generating unit into operation. So when you are taking any power generating unit into operation, now when you are taking power generating unit into operation, all the technical procedures of synchronizing that unit to the grid and start delivering power to the grid is to be done. So this typical operation is being called as commitment. So whenever you are taking any unit out of operation, that you will decommit the unit. Now then we can focus on what is the statement of unit commitment. The statement of unit commitment is, imagine there are n number of power stations, out of which you are making a small subsets, and those subsets can satisfy your demand in the system, and that is also economically. And this brings the difference between your concept of economic load dispatch and unit commitment. Concept of economic load dispatch you have already gone through, and there we have seen for economic load dispatch you are applying some optimization to the unit operations which are already in operation. So here comes the difference, because for a unit commitment is nothing but bringing unit operation or taking unit out of operation. Economic load dispatch is applied only to those units which are in operation. So here one thing you must have understood, when we are bringing some units into operation or we are taking out those units out of operation, so there will be definitely some constraints on these bringing in or taking out. So now these constraints can be differentiated from case to case. Even individual power plant can also have its own constraints depending upon its load cycle and its overall strategy to supply power to the grid, availability of fuel, its location, and all these constraints are over there. But we are going to consider in this lecture there are typical 2 3 constraints. So one of the very important concept to be discussed is spinning reserve. Then we'll discuss thermal unit constraints, and then some other constraints are over there which will include your hydro constraints also. So very important concept, spinning reserve. This is one of the very important ancillary service also nowadays being considered. So what is the definition? You can put this in terms of formula. So this is total amount of generation available from synchronized units. So this is what I was discussing in the concept of unit commitment. Now what has happened? Now you have brought units into operation minus present load plus losses. So this is the definition of spinning reserve. Then how to allocate spinning reserve? Now a spinning reserve by concept is a kind of energy which will be available as and when required. So your units are already in operation and there is some reserve available. So whenever system will demand it, you can immediately put that power into the grid. Now And how to allocate this spinning reserve? So this allocation of spinning reserve depending upon the different criteria. So some of the important criteria I'm putting in front of you. The very important criteria is percentage of forecasted peak demand. So there is always, you are aware of, the load forecasting is over there. So if my peak demand is going to be there after some 2-3 hours, and then how, who is going to share that peak demand is a very important concept. So load is not only put on a single plant. Instead of that, every plant shares some amount of power from each and individual capacity, and that is nothing but the contribution of spinning reserve from each and every plant. So this allocation of spinning reserve is done in proportional to the percentage of forecasted peak demand. Another spinning reserve allocation criteria is, it is ensured that the spinning reserve is uh, available considering the loss makeup of most heavily load. So imagine some load is demanding a lot of power, and suddenly some thermal power plant goes out, or some very heavily loaded plant goes out. Then it is to be ensured that some spinning reserve is available, which will ensure the frequency stability of the grid. So that is why I said at the start of this explanation of spinning reserve, this is one of the very important ancillary service, because it is supporting nowadays for keeping your system frequency stability. Uh, Another thing is, you can calculate spinning reserve and depending upon your probability calculations. So probability used for load forecasting as well as probability used for generation forecasting. So considering there will be some insufficient generation after some time, or considering some particular time period, you have to ensure that generation is being replaced by some other uh, generating capacity. So from generation side as well as from load side, you have to ensure that your system is going to be balanced. So generation is equal to demand. Not only this, your spinning reserve can be allocated considering the time constants of the various technologies. Like there are some units which are supplying energy faster. There are some units which are having slow response. So considering that, balance is to be brought into the system. This is about spinning reserve, but there are some other reserves also, like scheduled reserve, which is also called as a offline reserve. Now this, when you are calling this as a offline, spinning reserve you can definitely call as a online reserve, because it is immediately available. Now for scheduled reserves, the concept is, these units are not connected to the grid, but they can be brought immediately into the operation. For example, which in terms of power generation technology, you have understood those as peak load plants, like pumped hydro stations, hydropower stations, or some other technologies which are coming into the operation immediately. So which is quick start units, and because they are quick start units, you can consider them as a reserve energy stock, and whenever there is some supply demand imbalance, you can immediately bring those into picture. Last but not the least, how to spread the spinning reserve throughout the system. And the concept is, you have to consider two concepts. One is bottling, which is transmission line congestion, as well as islands. So what is transmission line congestion or bottling? Imagine you are keeping all the spinning reserves at one side of the power system, and some requirement comes at the other side, then definitely there will be uh, some transition line congestion will be there. As well as, that is why what you are doing, you are keeping energy storages distributed, so that even if some major issue is there in power system, you can form individual islands, and after that problem is solved, you can bring uh, all these islands together to form again a single grid. So this is the concept of spinning reserve. Let us consider some thermal unit constraints typically for thermal power plants. The characteristic of thermal power plant is, it once it goes out of operation, uh, a lot of time is taken to bring back into the operation. This is because of its principle of operation, which depends upon the temperature achieved in the boiler, steam generation, and then steam thrown on turbine. You have already learned these concepts in power generation technology. So because of this time constraint, it cannot be started immediately, like you are starting the plant and it has started giving you power. The time is very important, so there are some constraints. Minimum uptime. So how to understand this minimum uptime? So just consider uptime. So the here unit has started. So after unit has started, there is some minimum time before which you cannot turn off the unit. So this is constraint. In a reverse way, if unit is down, you cannot immediately start it. So this is having a typical time constant for thermal power plant, and which is generally a slow response. Now there is another constraint related to manpower. Imagine, I'll take an example of our own Nasik Eklare plant, where more than one units are over there, and two units go off simultaneously. And you want to synchronize both units. There is a requirement of manpower in thermal power plants because a lot of complex systems are over there, and then because of limited staff, you cannot start both units simultaneously. So that is called as a crew constraint. Apart from this, as we have already discussed, thermal power plant is having uh, some time lag to start actually supplying power. So whatever power is wasted from zero till it achieves that particular condition where it starts supplying power, whatever power loss is there in terms of megawatt, which is not useful for grid. So this operation is called as a startup operation. So cost related to this is called as a startup cost, which is also considered in unit commitment. So this is also one constraint. And then for all thermal power plants, when you are doing some maintenance or you are doing some unscheduled outages, uh, there is change in your capacity limits. So this constraint also you have to consider. So I'll again repeat, for thermal power plants, you have considered uptime, downtime, crew constraint, startup cost, and capacity limit. Let us consider some more constraints, which are other constraints. Now, majority of the constraints are for thermal power plants, but when you are considering other technologies like hydro, you are aware hydro is uh, all operation depends upon availability of water. So water, the same water we are using for agriculture, same water which we are using for domestic purposes also. So there are some constraints on hydro units, how you can schedule those. So though they are fast responding, you have to have the scheduling of hydro units is somewhat complex, and that constraint you have to consider in this unit commitment. Another constraint is, and this is typically nowadays we are facing problem, I will share, because there are some units in your operation which must run throughout the year, or they must be in operation 24 into 7 because of requirements. Now what are the requirements? Because some of these units are giving some voltage support to a transmission, or there are some cases where steam being generated in boiler is also being used for some other purpose. So these are the two constraints. Nowadays because of technology, we are giving some must run status to some technology plants like solar PV and wind, because uh, they are of intermittent nature, there is no presence of prime mover. So the aim of grid or a controller's aim is to extract maximum power from them, and we are using the technology of maximum power point tracking. So now they are enjoying the must run status. So nowadays even this solar PV and wind, uh, because of government rules and regulation, they are enjoying the must run status. So this is also constraint. So why this is constraint? Because you have to keep some units on continuously, and then you have to manage this supply demand balance. And here the question again I will repeat, you want to bring some units into the operation. So while calculating these things, you have to consider first how many units must be in operation, and then calculate its economical part. And last but not the least, There are definitely constraints on uh, some fuels of the plants where either there is limited availability of fuel or utilization of fuel in a certain time is required. So these kind of technical constraints are also there. So depending upon that, you have to calculate the problem of unit commitment. So unit commitment is definitely a mathematical problem which is to be solved by different methods, which is going to be a part of some of our other lecture. But in this lecture, what we have done, we have already understood the concept of unit commitment. So I just revised that, and we had now understood what are the different constraints which you have to consider while solving the problem of unit commitment. Whatever you have understood throughout this lecture, you are welcome to discuss on my Padlet created. Please ensure you are writing your queries as well as conceptual understanding in the column of unit commitment. And for this concept, I would like to recommend only one book which is very good, Alan J. Wood and Wollenberg, the title Power Generation, Operation and Control by Will India Edition. Thank you.